Okay, so now we're going to talk a little bit about the notes for section 11.2, which is mostly about um, things underlying Bohr's model of the atom. Okay, we do have a homework assignment that's associated with this. It's 11.2 questions 1 through 6. And the objective today is to really sort of master energy levels in Bohr's model of the atom. First question is, what is the ground state of an atom? The ground state is the state where all the electrons are in their lowest energy, most stable positions inside an atom. So, for instance, the closest to the nucleus, the energy level that's closest to the nucleus, corresponds to this lowest energy state. So you will see that each energy level can only hold so many electrons as we go along farther in this unit. Now, Bohr noticed that the spectral lines of hydrogen are always specific wavelengths. So if you look at the visible wavelengths, they're always the same. If you look at the infrared or UV wavelengths, they're always the same. The question is, how can this be accounted for? So this looks like the spectra that was on your little worksheet. You can see there were 4 wavelengths associated with the hydrogen atom, all right? Now what Bohr did is he came up with a first quantitative mathematical explanation for this behavior. He actually came up with equations that would predict the wavelength of all the visible bands, all the UV bands, all the infrared bands that were emitted by a hydrogen atom when you're bombarding it with energy, and you could see what energy was coming back out. Now, the energy I's behind his model correspond with that atoms normally exist in what is referred to as a ground state, lowest energy, very stable state. Atoms can absorb energy, and electrons can move between energy levels to get excited, so move to an excited state. And when they drop back down to ground state, they emit energy. The key thing is the energy changes are quantized. This means only certain transitions are allowed, and the transitions for every single atom are different. They're different distances apart in terms of energy, so you will end up with a unique fingerprint of emission spectra for every single atom. Okay, so during excitation, energy is absorbed by an atom. So again, we're just talking about a hydrogen atom here. So here's your one electron, here's the nucleus. Some energy comes in, boom, hits the electron, and there's enough energy for it to jump. So this has to be enough energy so it can actually go all the way out to the 3rd energy level. Now, it went from the ground state, out here it's in an excited state, okay? Now, suppose the amount of energy coming in was so little that it couldn't even get it to the second, from the 1st to the 2nd energy level. Nothing would happen. The light would just pass through. No energy would be absorbed, okay? If energy comes in and it's even greater than it takes to get to the 3rd, but not enough to get to the 4th, it will end up going to the 3rd. You cannot go in between. You can't go to level 3.5. And the other thing is any leftover energy would pass through, but the energy that was absorbed would be exactly equal to the distance between the ground state and the 3rd energy level. So, like I said, all the transitions equal to the energy difference between energy levels are possible. There is one exception, but it's sort of weird. If you hit it with enough energy, you can actually move the electron so it will actually come out of the atom and form an ion. Now, it's not a stable state, but you can actually remove electrons from atoms if you hit it with high enough energy wavelengths like X-rays or gamma rays. Okay, emission is the energy that's emitted. Now, where does that come from? When you jump down from a higher energy level closer to the nucleus to a lower energy level. Remember, this is like when I was jumping around on the ladder. So I was going from like the 3rd step to the 2nd step, or 2nd step to the 1st step, or down to the ground. Let's call the 1st step the ground would be more appropriate. There's differences in energy here. And so when things jump back towards the ground state, energy is emitted in the form of electromagnetic radiation. Remember, energy is never lost from the universe or from any system, all right? Any energy that was absorbed when it knocked it from the 1st out to the 3rd is going to be emitted. In this case, some of it will come from going from the 3rd to the 2nd, and the rest will come when it comes back down to the 1st. We never actually lose any energy. And the energy emitted will equal the energy difference between the energy levels, between the jumps. So we can actually predict what wavelength of light would come out if we know the energy here and the energy there. Now, the hydrogen spectrum is based on this discrete set of changes. So the way it works, as you're going to find out, is each energy level essentially corresponds to a period in our periodic table. The energy emitted, this electromagnetic radiation, it comes out as visible light. Depending on the jump, it might come out as infrared light, or it might come out as UV light. Again, this is just the hydrogen atom. So these discrete changes in emitted energy are visible to us as that line spectrum of hydrogen if we're looking at only the visible range. Now, that visible range of light coming from hydrogen is called the Balmer series. The Balmer series are electron jumps from the outer energy levels in the hydrogen atom down to the second energy level. These transitions result in this visible line spectrum. So we see 4 lines. We're talking third to second, fourth to second, fifth to second, and sixth to second. So those are shown here. Those are the lines that we can actually see. Now, you notice that there's also transitions that end in the third, and there's transitions that end in the first. The ones that end in the third are smaller energy, lower energy. They're infrared. They're off the red end of the spectrum, so they're lower energy. And the ones that are very large, those are the Lyman series. Those would be ultraviolet energy. And again, these 4 bands correspond to these 4 bands. It's too bad that that green doesn't match the teal there, but it's close enough. Now, in Bohr's model of the atom, here's what you need to know. It's got a tiny positively charged nucleus. That's the same idea as Rutherford's model of the atom. Makes perfect sense. Electrons orbit the nucleus in concentric rings similar to a solar system. This was a unique idea of Bohr's atom, and that each ring is a fixed amount of energy apart, he calls them an energy level, from each other. And in other words, they are quantized. They're only allowed to have certain numerical values. The rings get closer together as you get farther from the nucleus. So you saw that in the one big picture that I put out there. Now, electrons are held in place through electrostatic attraction to the protons in the nucleus, and they're kept from falling into the nucleus through centrifugal force, momentum, which balances the attractive force. So it's just kind of physics. Now, unfortunately, Bohr's model pretty much only works for the hydrogen atom. It fails as soon as we get 2 electrons because it doesn't take into account that electrons repel each other. Schrodinger's atomic theory you're going to see is right now is a perfect explanation of the behavior of electrons inside atoms. There was one intermediate between Bohr and Schrodinger, and that was de Broglie. De Broglie showed that electrons' behavior inside atoms is most like a wave, not like moving on a ring, like on a line on a ring. So modern atomic theory states, this is Schrodinger's theory, that electrons are found in energy levels described by a wave function. So this is a calculus equation, based equation, and that every electron in an atom has a locational probability. They're not at any one specific point that we can identify at any given point in time. We can only describe that there is a probability they are close to that point. This probability is described by the square of the wave function. We are not going to do the math here. Basically, this is a very higher level quantum mechanical explanation of what's going inside an atom. So you're talking a higher level chem course or even a graduate chem course to really understand this. And you've got to have a lot of math in order to get it as well. So here's really what the upshot of Schrodinger's atomic theory is. We don't need to know the basis other than that it basically provides a model where electrons move like waves, and they are in 3D regions of space around the nucleus in what we call atomic orbitals, not rings, and that electrons have a probability of being found in an orbital at any given point in time. Now, if you go watch the PhET video right now, all right, the one that I saved, when you get to Schrodinger's atomic theory, you will not see rings. You will see that when the electron goes from the ground state to an excited state, there's sort of a pattern of different locations in space it could be. The ones that have the highest probability are brighter, and the ones that have the lowest probability are dimmer. But it basically shows where, in general, the electron could be found, but it can't show the precise location.